Good afternoon, fancy meet computers, to this, your Computer Science 3 Mission Impossible 3 course. Yoink. Bloop. My cat wants attention, so I'm going to give her some attention. And you guys can pay her some attention too. Look how beautiful she is. You're a beautiful cat. Oh, you're a beautiful cat, Rimbushkina. Look at the fluffy tail. Look at the fluffy tail on this cat. It's amazing. Whoop. There we go. Alright. Bloop. That will suffice for our is the stream working check today. How is everybody doing today? I see I have 11 concurrent viewers. That's not as many as I would hope for. Sometimes sometimes it just takes a while for people to get in. Thank you. She is a nice cat. Kind of demanding, though. You know how they can be. Mathlic versus Matheist. Yes. Mm-hmm. Yeah. Mathlic works pretty well as a pun, actually. Trying to think of other ones. Orthogonal docs. And one for Protestant. Come on. Periodistant. That would be a chemistry pun. I'm so sorry. I broke it. So, is there like a test today or something? Like, where are y'all? Yeah. Hello. Welcome to the stream. Welcome to the stream. 3 assignments due this weekend. Oof. Oof! Well, it's a good thing I pushed P1 back then, eh? Originally, Project 1 was due this weekend, so, yep. Yep. Good thing we fixed that. Yeah, if you want to, like, align a series of equations in LaTeX, you should just do what I do, which is use the tabular environment and use, like, equations in math mode inside of the tab cells and just don't put lines in. That's the easiest way, in my opinion. That's actually what I'm doing in, like, if you take a look at the text source for this set of lecture slides, I do that a lot towards the end. That's part of the reason that I've been including the text source for, like, the assignments and the slides and such, is so that you guys can, if you wish, peruse the text source and see how I'm generating my equations. How is Project 1 coming along? Have you guys worked on it at all? Or, are you guys, like, still getting killed? Align is nice. Yeah, I do like Align. I've actually been using it for the first time this semester. And, yeah, I have to say it's pretty nice. I haven't really taught a course that requires this many equations before, so I'm learning a lot, too. I try to minimize instances where it's like, oh, this is too complicated. I'll just copy it out of the... I'll just do an image off the PDF. Do a screen capture. I did that for the semantics, because it was like, man, I'm just going to copy this. You know? I got deadlines. We all got deadlines, but I got deadlines too. Still learning Haskell. Good, good. Just have part 3. Everything else is getting in the way. Yeah, that's kind of the way of it. Not yet. Stuck on... Oh, yeah. Okay. You know what? I'm going to do a poll while we're waiting for more people. What part of P1 are you on? 1A, 1B, 1C2. Oh, I can only do 4 options. That sucks. Bloop. Honk. There we go. 3SD3 assignment is a grind and a half. Meh. Cool. Well. Yeah, that's kind of the way of it. Nobody does anything until it's the deadline's on top of you. And, you know, I get it. But, you know, hypothetically speaking, you know, it's easier to do these projects if you do them, like, one part at a time over the course of, you know, a couple of weeks than to try to cram it all in for the deadline. Like, you'll definitely end up requiring more time than you have, which means you'll be working at, you know, a faster pace than you should be, which means you're just causing yourself stress and likely to make errors. So, you know, but hey, I know what it's like, you know? Cool. Anyway, might as well get on with it. Get on with it! Alright. So, recall last time, we covered quite a bit of ground last time. We were talking about lambda calculus. We were introducing the idea of lambda calculus. And lambda calculus, just to recap, is a very different way of thinking about computation. We're defining computation exclusively in terms of functions, function application, and what this new idea that we have now of argument extraction or abstraction. I'm probably going to say extraction and abstraction interchangeably over the course of this course, so it means the same thing. But yeah, we've got this lambda operator now, which allows us to abstract a variable out of an expression, which is very cool. And like, presumably you guys have dealt with function application before, so that's the new thing with lambda calculus. But it's not necessarily intuitive how lambda calculus actually calculates things. So that's what the rest of the week is going to be, is like working our way through some examples of how the lambda calculus actually operates, some concrete examples. You can see towards the end of this, we're going to be dealing with how to implement booleans and how to implement numerals. I just gave away both of my comics. Ha! There you go. There's another one for you. Does each section have an intro comic? One. No, basics doesn't. So, so we're going to go through some examples of how this thing actually works, why it's practical. I just want to point out, once again, for the record, this is the way that Haskell does everything. In Haskell, everything reduces to lambda calculus. So it can be used to support an actual fully fledged programming language. This isn't just a toy example. This is used practically in the real world for stuff. And interestingly, functional programming, sort of as a general category of programming, has been expanding over the last few years. It's still a pretty highly specialized thing, but the big guys are now like doing parts of their doing parts of their code bases in functional programming now. Particularly, I know that the Facebook anti-spam algorithm has been written in Haskell. So, there you go. Functional programming. So, let's talk about the semantics of lambda calculus. Remember, everything's based on substitutions. So, each execution step in lambda calculus performs a function application on a term with at least one abstracted variable. So in order to have a step that you can compute in the lambda calculus, you must have one of these guys, right? So you're extracting a variable over some term t. This as applied to with a function application. So if this term here is this guy, then all instances of this term get replaced in all instances of x in this term get replaced by that term. That's the semantic of that's your one evaluation rule. So it's kind of cool because you really only have the one evaluation rule in the lambda calculus. Yes. This means both a lambda and an abstraction and a function application must be present and adjacent for a term to be reducible. These terms reduce by substituting the abstracted variable with the term applied to the function. In other words, lambda x over y over t1 with t2 applied becomes x replaced with t, or x becomes t2 in t1. This is the syntax we'll use to indicate a replacement operation or a substitution operation. A lambda expression, which may be simplified, is known as a redex, or reducible expression. So, this is a redex. The above evaluation process is known as beta reduction. So, when we say that there are reducible expressions within this term, we would say, this term has 6 or 7 redexes. To get from one term to the next, we perform beta reduction. So again, this is essentially equivalent to our concept of the evaluation relation, or in untyped expression language, UAE, untyped arithmetic expressions. Pardon me. So, using all our substitutions. In the previous slide, the symbol square braces x becomes t2 on t1 stands for the term obtained by the replacement of all free occurrences of x in t1 by t2. We will eventually need to define two sets of operational semantics, one for rewriting lambda expressions and the other for performing substitutions. So we're not going to get super rigorous with this stuff just yet. We're going to hold the rigor for topic 6, essentially, because it's important to sort of develop the intuitions related to lambda calculus before we begin introducing the the formal mathematics of it, which, and start proving theorems over it. Like, it was appropriate for us to immediately start into proving theorems for expressions, because everybody should at this point know what an expression is and how it evaluates. You should have a good intuitive feeling for it, but you don't necessarily have a good intuitive feeling for lambda calculus, because you guys, probably you've not programmed in Haskell very much, and all the rest of it. So here are some examples. Lambda x dot x with y applied, that yields y. So if we take this, we're applying y to lambda x dot x. So x gets replaced with the argument y, which also makes the lambda expression go away. So all you're left with is y. So there you go. Very simple. The next one, we've got lambda x dot x. And then lambda x dot x is applied to x, right? Space is always function application. So we're applying this lambda expression to x, right? And to all of that, we are applying u with r applied to it. So r applied to u is being applied to this larger expression. The result of that is we get u with r applied, and then we apply lambda x dot x to that, right? This guy right here gets substituted in right there. And the lambda goes away. Note in this last example that the substitution operation does not pass to the inner lambda expression. Notice we substitute ur here, but not here. This is because occurrences of x inside of this expression are not free, but bound to the containing abstraction. So this is not a free instance of x. You kind of delete this lambda, and then, then once the lambda is gone, you evaluate which x's are bound and which ones are free. And that's how you proceed. Kind of like this intermediate step where we have explicitly stated the substitution operation, we're not often going to actually see that printed out. It's going to be implicit in a lot of this, but just, keep in mind that before we determine if it's bound, we remove the lambda that we're going to be removing eventually anyway, and then we determine whether or not any of the x's or y's or any of the variables are bound or not. Question. Hypothetically, would you not simplify ur first in the order of operations? No. Well, okay. So your question is relating to the concept of evaluation strategy. One of the problems that you may have noticed, that actually Yusuf has noticed, is that this defines a substitution, but we have a problem. A lambda expression may have multiple possible evaluation steps that you could undertake at any point in time. So, essentially, lambda calculus, the beta reduction process of lambda calculus is not deterministic until we have applied a evaluation strategy to it. So the next few slides we're going to talk about evaluation strategies. But yeah, there is one kind of sneaking little problem though with what you've pointed out there, Yusuf. Could we not evaluate ur first? ur does not evaluate, right? In order for ur to evaluate, would have to we would have to have u defined somewhere else as some expression that contains a lambda at the top level. If it doesn't contain a lambda at the top level, that means it's in normal form for lambda calculus. So ur, taken by itself, is already in normal form. We cannot evaluate this sub-expression any further. And the same is actually true for lambda x dot x. This is also in normal form. And within this expression, this is also in normal form. So really, it looks like there might be multiple evaluations that you can perform with this particular lambda expression, but it turns out there isn't. There's just one, and that is the application of ur to this lambda. Does that make sense? Have I lost you all yet? Give me a thumbs up if you guys are following, okay? Or, good so far? I just did a poll. Good. Evaluation dilemma. Okay. Well, if it's not good so far, please ask me a question, and we will try to improve your understanding. Okay. Okay, so it's just people with fast internet that said no. Primarily. Okay. Yeah. So, it's kind of part of the education process at this point. If you don't understand it, please ask a question, right? Could I explain again how 6 was evaluated? Yes. So, I think it might be easier if I do it, like, on paper, so to speak. If I had a chalkboard, if only I had a chalkboard. So, there we go. So we've got, I'm pretty sure the lambdas aren't going to come out. Oh, they do! Wah! There we go. All right, so to evaluate this expression, we have one evaluation step that's possible, right? We are applying this expression to this lambda. So, what do? We delete the lambda. We look at inside of here. We can also delete the parentheses in this case as well, just for cleanliness. We look at this expression. We say, okay, how many free instances of x do we have? We have this free instance of x and no other free instances. So we copy, paste. And that is lambda application. So, another question. So if the inner lambda x dot x was simply x, then would be put in both instances of x. Yes, that's correct. That's correct. So the case that your colleague is talking about is if we had x, then yes, the way that this would get evaluated is we remove the lambda, we look at all free instances of x, right? We copy, paste. Oh, I copied, actually. It doesn't matter. It ends up looking like that. You are. My understanding of evaluation is that we take the furthest left lambda and the furthest right parameters and do that substitution. Yes! Yes, that's a good one. That's a good approximation of it. As we're going to see, like, things get a little bit more complicated, but it's good to hammer this out before we get to the next bit. So, like, we're going to take it slow, right? We're going to take it slow, and we're going to actually understand things before we move on to the next thing. Hopefully, that way we can build up our knowledge effectively. So good. But that absolutely, once again, this absolutely relies on you guys asking me a question when you don't understand, because I can't see your faces, so I don't know if you guys are all like, huh? You know, normally if it's an in-person class, I can look at your faces and see if you're, you know, understand what I'm saying, but not in this case. Anyway. So, evaluation dilemma. So far, we have had a reasonably rigorous definition for beta reduction, and our intuitions about substitution derived from high school algebra classes. Yes, so it's like... It's very much like if you had an algebraic formula, like two algebraic formulas, you manage to solve one so that x is 7, and then you replace all instances of x with 7 down below, that plus the scoping rule, and you're good, right? The goal is to be able to create an algorithm which evaluates lambda expressions. Fundamentally, eventually, we want to be able to encode this in a computer. That's the whole point! So, what happens if we have a choice of multiple beta reductions in a single lambda expression? We need an evaluation strategy, which we can build into our operational semantics. So we have not yet approached the problem of the order in which things evaluate. Now, in untyped expression language, or untyped arithmetic expressions, we had the same problem, right? But we kind of glossed over that problem by introducing semantics which impose one particular way of evaluating things. The Backstreet Boys, really? Come on, guys. I'm old and I'm too young for the Backstreet Boys. So, yes, we need an evaluation strategy. So, let's consider the following lambda expression. We'll use this as a running example because it has a few different redexes which we can beta reduce. So, incidentally, x.x, lambda x.x, is essentially an identity function. What we mean when we say identity function is it's a function that takes something in and then spits the exact same thing back out again. Identity function. So, rather than, repeatedly type this all the way through, we're going to call it ID. So, essentially, this guy is ID of lambda z ID z. So, in effect, in this guy, there are, yes, I got it. I know. I got the pun. I got the pun.
I'm laughing on the inside.
So, the above expression has three possible beta reductions. There are three redexes. So, the top level one, right? The identity as applied to the rest of the function. We have a middle identity that could be evaluated. And we have this smallest one inside of, past the lambda. Cool? The question is, which of these do you do first? And then which one do you do next? We need a strategy, because if we don't have a strategy, the correct answer is all of them, possibly. We want it to be deterministic, right? We must maintain the principle of determinacy. So, here's the worst strategy, by far. Full beta reduction. Under full beta reduction, the redexes may be reduced in any order. It's not really even a strategy, because a strategy makes... in order for something to call itself a strategy, you'd think it was it would have to make a decision. And the strategy here is you make the decision, and that's not really a strategy. So full beta reduction is not even really a strategy. This algorithm is non-deterministic. And this is kind of small print, but I'll zoom in on my meme here. But there are probably mathematical applications where you need a strategy like this to ... Can't implement, no point. Normal order. So we have had normal forms, now we have normal order. Normal order begins with the leftmost outermost redex and proceeds until there are no more redexes to evaluate. This is the way that a human would probably choose to do it if they weren't thinking about it too hard. So, under normal order, you do the first one first, that is to say, the outermost ID. Then you evaluate the second one, because that's what you're left with. You evaluate this guy. And then you have this left. You evaluate ID z, which is, of course, just z, which is, again, the identity function, incidentally. But that's the end. There are no more evaluations past that point. Under this strategy, and those to follow, evaluation is a partial function, as each term, t, evaluates to at most one term t prime. So because we now have a strategy that is exclusive, it picks 1, we have reachieved determinacy, which is our golden property. We also have call by name. The call by name strategy is more restrictive than normal order. You can't evaluate anything that isn't an outermost term. In this case, ZIDZ is considered to be a normal form, which is kind of interesting. So, under call by name, this guy, the first guy executes, the first regex executes, the second regex executes. Up to that point, this actually, for this one, it looks very much like the normal normal order. But once you hit lambda z idz, you have an exterior lambda which is not it's no longer evaluatable, right? There's no argument that's being applied to z, so it stops. What this essentially means in terms, to put this more in programmatic language, if you're left with a function that still needs arguments, you stop. That's what that means in Haskell terminology. In Haskell, if you undersupply a function with arguments, that's actually a legal operation in Haskell. It's a very legal operation in Haskell, actually, to undersupply a function with arguments. What you get as a result is a function that requires fewer arguments, with the appropriate beta reductions having been applied, right? So, so in Haskell, as in lambda calculus, as in lambda calculus according to the call by name strategy, this is where you would stop evaluating. So this is a normal form. I'm going to ask if that's good so far again. And while you're answering that, I'll bang on about Haskell a bit. So, an optimized version of the call by name strategy is called call by need. And this is the one that's actually used by Haskell to evaluate expressions. So it's like call by name. It follows the same essential pattern as call by name, except it does some extra stuff as well, which performs optimization. So in order to avoid having to reevaluate the arguments of expressions, which is a big problem in a functional language, because functional languages don't hold state in the same idea that, it doesn't have the concept of state that you would have in an imperative language. So it's not like you can just hold on to an intermediate result and, store it in a variable, get it back later. That's not how functional languages work. So this is what they do instead. Haskell overwrites all occurrences of an expression the first time that expression is evaluated. So all occurrences. So whenever in Haskell you have an expression that evaluates to some other, some final result, or whenever you fully evaluate something, it goes through all the rest of your functions and flips that out for its result. As a result, any expression only needs to be evaluated once for any particular run of a Haskell program. Effectively, this is a reduction relation on syntax graphs rather than syntax trees. You can think of it as, rather than having syntax tree, each function has a syntax tree that constitutes that function. But if you conceptualize a graph that hooks all of the function abstract syntax trees together, you get a forest. That's actually what the term for a group of trees is in mathematics, is a forest. And you can perform operations over the forest and not just the trees. So that's kind of cool. It's not you don't have to know that for this course, but since you guys were learning Haskell, I thought that might be interesting to you anyway. So, call by value. So this is our third evaluation strategy that isn't garbage. Most languages use call by value, where only the outermost redexes are reduced, and a redex is only reduced when the right-hand side has already been reduced to a value. Here, as elsewhere, a value is a term in normal form. So call by value is kind of how your conventional imperative language or object-oriented language would handle the issue of function evaluations. Oh, 2CO3 covered forests. There you go. You'll know exactly how wrong my description was then. So, think about how the order of evaluation occurs in something like Python, right? In Python, you don't execute the function until all of its arguments have been evaluated, right? Like if I were to call, if I had an add function and I was going to add the sum of a list to, the length of a list, right? Python evaluates the sum of the list first, then it evaluates the length of the list, and then it passes both of those to the calling function. So you get like a certain amount of step inside with respect to it. And since this is an imperative again, they've been putting more functional type stuff in there, but like if you think about a programming language like C, then if you don't supply a C function with enough arguments, that's considered to be an unevaluatable normal term or a normal form. Just like, it's kind of like the type of error term we would get in UAE by passing true to successor, right? It's like, this does not compute, cannot be computed further. So yeah. So that's call by value. We will be using this strategy a fair bit because it is commonly implemented in programming languages, and it just happens to be easier to enrich with added features, which is a thing that we're not really going to be worried about too much today. We're going to be worried about that more so in the coming time in the coming lectures. But yep. Any questions? Looks like most people are following along. Good. Curry in a hurry. So, you may have noticed that so far, our functions have only taken one argument. It would be almost trivial to define an extension to our calculus which allows multiple arguments. Like, you can easily imagine how we would define a function to take multiple arguments, right? You would have, copy x, y, something. That would be how you would do multiple arguments, right? You could imagine, like, pretty easily, you could do some kind of syntactic manipulation that would yield something like that. You'd have your argument, you'd have your expression, your term, and then to that you would apply something like, you are with a comma there. That would be sort of like introducing pairs or tuples. We don't really need to do this. It's not necessary to do this in our basic lambda calculus because, as is the case with Haskell, when you apply one argument to a function that takes multiple arguments, you get a function that takes one less argument, right? That's how functional works. That's how lambda calculus works. That's called currying. We don't have to because of currying. So the term currying is derived from the name of a guy. His name is Haskell Curry. That's his real name. And He's the guy who they named the Haskell programming language after. They were going to name Haskell Curry originally, but then they thought there would be too much confusion with existing uses of the term curry, so they called it they named it after his first name instead. So they called it Haskell. Interestingly, Haskell Curry denies having come up with the idea of currying, although it has in the past commonly been attributed to him, and has actually it's been named. It takes his name, but he didn't invent it, which is kind of an interesting thing. But anyway, because our functions are higher order functions, that is, they can return a function as the result, we can describe a function taking multiple arguments as a series of functions taking one argument that pass their result to the next. Here's an example. Coconut lamb curry. Lamb korma. God, I miss eating Indian food in restaurants. Takeout is not quite the same. So, this is how we might pass multiple arguments in a richer language. We would have lambda xyz, and then some term s. We apply to it abc. We get a replacement x for a, y for b, and z for c. It was his namesake because people were hungry. Yes, and all of those replacements applied to s. So you have this interesting property where, within the statement x, or within the term s, x, y, and z are going to, well, I was going to say a thing that probably might not be the case, so I'm just going to hold my tongue. Never mind, I'm not going to say the thing I was going to say. So, and you'll never know what it was. In our calculus, the following statement is equivalent. So if we have lambda x, lambda y, lambda z applied to s, and then we apply a, b, and c to that, we get on our first evaluation, we blow out the first lambda, perform that substitution on s. Then we perform another beta reduction, blow out the second lambda, end up with 2 substitutions on s. Assuming we haven't performed the first one. This is just to indicate, like you would actually perform the substitution. But and then, of course, our final argument c is applied to z, is applied to lambda z, and we get z gets replaced with c. There we go. It should be noted that in our untyped lambda calculus, it should be noted that our untyped lambda calculus has not been designed for use by general programmers, but for greater simplicity in proving mathematical properties. So, what am I saying when I say that? I'm saying when you want to program practically, you're going to need something a bit stronger than lambda calculus. Like, you're going for the sheer sake of practical consideration, lambda calculus is insufficient. You would never get a job programming in lambda calculus, is what I'm saying. You could hypothetically get a job programming in Haskell, but Haskell improves and extends lambda calculus sufficiently that it becomes, useful. You can write programs easily in it. It's not easy to write a program in pure lambda calculus because it's too long and there are too many parentheses. As you're going to see when we get into numerals, these things have a tendency to descend into parenthesis hell. So, yeah. So anyway, that's a little bit about the semantics. Good. How are you guys doing? Going to ask you again. Still following? Next, we're going to get into church booleans. Let's see. Yeah, everybody seems to be doing okay with this. Y'all are too smart. Too smart! Good. Okay. So, don't worry, things will get complicated. Strong like Boole. Now, we have a new mode of computation established. The next most logical thing for us to do is to just we just have to ruin it with all of our old constructs. So Arrow has a question. You can write it ABCS. No, in this particular case, like, if this expression would actually be, this would, assuming S isn't like a name for something else, and like you couldn't expand this, then the result of this would actually be just S. As we're going to see, one of the rules of evaluation of lambda calculus is, and we're going to get into this when we talk about Booleans, but if you have lambda x and y is not reducible or expandable, and you apply some argument z to that, that evaluates to y. So z. Again, we follow our same process. Lambda x is deleted. We look for all free occurrences of x in the leftover expression. There are none, so no substitutions are performed. So that's good. Is it possible to implement optional or variable length arguments in Haskell / lambda calculus? Variable length arguments. You mean like lists? Like, can you put a list in? Because yes, you can do lists. You'll notice that the way that Haskell defines lists is essentially using currying. It uses like the way that Haskell defines a list is, it's like 5 cons 4 cons 3 cons 2 cons 1 cons empty list, right? So like this is a list, but it's like successive applications of the cons operator, like variadic arguments. I don't know what a variadic argument is. Let me look that up. Variadic functions are functions that can take a variable number of arguments. Oh, I see. So like print is a variadic function. That's interesting. That'll be my word for the day, is variadic. Not in pure lambda calculus. No. Not in pure lambda calculus. Variadic arguments would break pure lambda calculus. There's probably a complicated way of doing them, but it would have to be pretty complicated. So I'm going to say no for now, and if somebody wants to prove me wrong, they're welcome to. Maybe I'll put that on the test. Implement variadic arguments in lambda calculus. Everyone will get 0. So, anyway. So let's talk about Booleans. Oh, we've got like 2 minutes left in class. You know what? That's not really enough time to get into Booleans. So I'll just leave this slide up. So, essentially, the way that we're defining Booleans is it's lambda t, lambda f. T, that's true. That's, like, anywhere we say true, we're talking a function that takes 2 arguments and returns the first. And when we say false, we are talking about a function that takes 2 arguments and returns the second. you may say to yourself, well, that seems pretty arbitrary. Why would true be the first and false be the second? Couldn't it be just reversed? And your professor would say, yes, absolutely. That is the convention, and it's like the direction that current. It's like how the direction that current travels in the electric circuit is actually it's directly counter the way that electrons travel in the circuit, because they thought that electrons originally had positive charge. But it doesn't matter because, it literally makes no difference whatsoever. So, in Golang, you would do func variadic vars interface return type, but it interprets that as vars equals interface. Yeah. Yes. Okay, I'm gonna look it up. Variadic functions in lambda calculus. Okay. So I found a scientific paper, a variadic extension of Curry's fixed point combinator. So I'm not sure if this is what we're talking about, but I think fixed point combinators are a thing that we're going to be getting up to, not something that we have available to us at the moment. But let's see. Let's see if we can. There we go. Well, it's important that you guys are following along, Where are the implied brackets for 13 and 14? Or does it depend on the evaluation method you're using? Well, it's just, it's the top level expression, so it doesn't need brackets, but you can put it in brackets if you want, Brackets are up to you. There doesn't really seem to be much for variadic functions in lambda calculus, so if it's in there, it's probably a language extension. Like, what you would need is you would need a lambda function. Like maybe you could get away with it with recursion. Maybe it's recursion. Maybe recursion is the answer. Yeah. You just need to think of variadic functions as containing an argument in which is a pointer to a section of items that, following a specific type signature, you increment the pointer to do the args. Yes. Yeah, but in abstract calculus, I see nothing. Yeah, it's one of those things where it's like you're talking about, sure, I know how I would implement that in C, but how would I go about constructing it in lambda calculus? When's the first midterm for this class? Well, I was only intending on having the one, but since you asked so nicely, I think we could have a second midterm. Why not? I'm not going to do a second midterm. I've got it scheduled for the October 30th. Saturday, October 30th. It will be from 9 a.m. to 9 a.m. the next day, because that's how I do tests. It'll be a take-home test, so you have aids. Aids are permitted, but no cheating. No cheating. Okay? Good lord, I need to start working on that test. Also gotta start working on the test for 2MP3. Two MP3 isn't that bad. Wait, what? Or is that W applied to A, is that T applied to I, applied to A, applied to W? November 6th? What? Why did you say November 6th? Wait, what? Wait, am I right? Am I dumb? Did I just do a dumb? I might have just done dumb. Oh, let me see here. Oh, yeah, because the week of October 31st would be the 6th, yeah. That seems like a long way out for a midterm. Like, are we seriously that worried about a midterm that's like more than a month away? Yeah, okay. I'll stick to what I said in the syllabus, because I'm nothing if not a man of my word. So, yeah. I guess everybody else is announcing dates for their midterms, right? That's what's prompting all of this midterm discussion. It was, wait, please don't make a second midterm. Yeah. Last week I said November 6th. Let the record show that your professor's brain is starting to go soft. Yeah. I probably did say November 6th. It becomes, like, the midterm becomes more manifest in my brain as I work on putting questions in it, so... Yep. Anyway. Yeah, if you look at assignment 4, it's mostly like no proofs in assignment 4. It's all just doing lambda expression calculations. And you have to do a couple of abstract syntax trees, that's it. Cool. All right. I guess if there's nothing further, I'll get off I'll get off the stream and let you guys get back to your lives. So, yep. Are there any further questions? You'd be surprised how little information they're giving on tests. Instead, they hide it in an updated course overview and don't announce it. Yeah, that's not cool. When the test, like, whenever a date is changed or set or anything like that, you'll get an announcement. I don't change or set dates without giving announcements for them. It's just not my style. Okay. Take her easy, folks. I'll see you on Friday.